Hey everyone, in our last video for this semester, we'll learn about some approaches to interpreting machine learning models. So let's start with an example of a data set where we may need some additional interpretation help. So this data set is called the Airport Survey data set. This example surveyed 5,000 customers about their most recent flight experience. This is real data, however, the airline which provided this data chose to remain anonymous. The goal here is to determine what factors of a flight experience are most related to customer satisfaction. So we have things like customer demographics, gender, age. We have things like the type of travel, whether they're traveling for business or for pleasure, the class of the flight, the distance, and then various items related to the flight experience. So, for example, how happy is the customer with their seat, with the food and drink offered on board, etc. So we'll start with just a single decision tree. Now you may notice that there are two categories which we're trying to predict. We're looking to see whether or not a customer is either satisfied or neutral or dissatisfied with their flight experience. Items or variables that are coming out of this decision tree: satisfaction with the online boarding experience, availability of in-flight Wi-Fi, and then type of travel seem to be important. Now we know that a single decision tree often is dominated by one or two variables, so we might build a random forest instead. It looks like we're doing pretty well with this random forest. Things to take away from this classification or confusion matrix: most airline customers are neutral or dissatisfied with their experience, but a few are satisfied, about a third are satisfied overall. Our misclassification rate is pretty low, about a 3% classification error for the neutral or dissatisfied group, about an 8% classification error for the satisfied group. Now, with this being a random forest, we can do things like look at the overall variable importance, but that doesn't really tell us the whole story. We might want to be able to answer a few more questions beyond importance of a variable, such as how does changing each variable impact the predicted values? We might also want to know how changing each variable ends up impacting the accuracy of our model. So we might like to dig a little deeper than just those surface variable importance measures. In general, we call this problem of trying to figure out what is actually driving the behavior of a machine learning model interpretability. This idea of interpretability is actually fairly new in the machine learning literature. One of the key references here is a paper released in 2017 that defined interpretability in the following way. Interpretability of a machine learning model refers to the degree to which a human can understand the cause of a decision. So how well do we understand what factors are really driving the prediction of the model? Another definition is the degree to which a human can consistently predict the model's result. So not only can we understand the cause of a decision, but given a new set of data, can we predict what the model is going to end up saying? Now, we have a trade-off in machine learning. Do we want to know what is predicted? So are we really focused on predictive accuracy of our model, or are we focused on maybe performing inference, figuring out why our model is making a certain prediction? Now, historically, if we wanted to understand the why of a model, that limited the approaches that we had available. If a machine learning model is interpretable, then we can check for the following properties. These are all things that, especially in the era of big data and surveillance and predictive analytics, these are all things that we would want to see in a machine learning model. First, we would want to see fairness. We would want to know that our predictions are unbiased and aren't implicitly or explicitly discriminating against particular groups. So a good example of this would be automated systems to determine whether or not somebody is qualified for a loan. Is that automated system, is that machine learning model that's being used making predictions or making decisions about a loan that are fair? Or is that model discriminating in some way? That interpretable model can tell you why it has made that decision. If we know why we have the decision, we can adjust for that learned, perhaps, bias or make the model more fair. Second property that we might want is privacy. We want to make sure that the sensitive information in the data is protected. We want to make sure that our model is reliable or robust. So we want to make sure that small changes in the input don't have too much of an effect on the change in the prediction. We want to, if we can, check for causal relationships. So we want to make sure that there are no spurious correlations or spurious relationships in the data. And then finally, trust. If we can explain what's driving the model or the variables that are important in the model, then we have better trust over the system. Now, there's a few ways that we can do this. One method that we can use to make sure that our machine learning model is interpretable is to strive for intrinsic interpretability. We get intrinsic interpretability from a model by restricting its complexity. We're looking for small models that have functional forms that are easy to understand. So things like logistic regression fall under that interpretability. Fairly simple decision trees also fall under that structure. So do k-nearest neighbors. We can look inside the model and really kind of tell what's happening. For other models that don't have this sort of nice interpretable functional form, we look to post hoc interpretability measures. So these are methods that we can apply after model training. These post hoc interpretability measures are what we refer to as model agnostic. So the actual model that's being used underneath does not affect how we're calculating these post hoc interpretability measures, meaning that they can be applied in any model. Things that we would like to see out of this. Obviously, model flexibility. We want this to work with any machine learning model. We want to be able to interpret random forests. We want to be able to interpret neural network predictions, things like that. We also want explanation flexibility. We also want representation flexibility. So we want to be able to use maybe different feature representations, maybe a simpler form of a model. So there are a lot of different model agnostic methods that are available to us. We can use things like partial dependence plots, individual conditional expectation plots, accumulated local effect plots. We can look at the feature interaction, global surrogates, local surrogates, and then Shapley-based measures as well. Most of these interpretability measures are visual in some way. So rather than getting a single interpretability score back, we end up producing some sort of plot to help us interpret the model. So we'll go through how each of these are constructed. I'll provide you with some sample R code to build them, and then we'll look at some examples of interpreting each of these. So let's start with partial dependence plots, or PDP plots. PDPs visualize the marginal effect one or two features have on the predicted outcome of a machine learning model. The way they do that is by breaking the feature space into two distinct subspaces. So X sub S are the features for which we'll plot the partial dependence. X sub C are all of the other feature inputs in the model. What we do is marginalize or take the expectation over the distribution of all of those other variables that are not represented in the partial dependence plot. So what this plot ends up showing is the relationship between X sub S and the predicted outcome averaged or marginalized over all other feature variables. The assumption here that's needed is that the variable that we're plotting, x sub s, and all of the other features in our model should be uncorrelated for this. So we're going to use a library in R to construct these plots called IML. IML is the Interpretable Machine Learning Library. The way this will work is that we'll start by building two data frames or two sets of data. We'll have our input variables stored as our inputs, our output or our prediction satisfaction stored as output. We then need to construct a predictor object. So a predictor object is just a way to define how we're going to make these predictions. And then we'll build our feature effect plots based on these predictions. So the code here is provided. You don't need to worry too much about how this code is actually being constructed unless you would like to incorporate this into your perhaps projects. Let's take a look at this partial dependence plot. So this partial dependence plot is actually visualizing the effect of two features on probability of being satisfied. So y hat here. The two features are the distance, so the number of miles for the flight, and then the class. We have business class, we have economy plus. There are two major patterns that stick out through this plot. Generally speaking, customers who are taking longer distance flights tend to be more satisfied. So if you're flying over a longer distance, you may be more likely to be a satisfied customer than if you're taking a short flight. We also see a pretty big difference in satisfaction rates, probably not surprising, between business class up here in red and economy plus down here in blue. Now there's not much difference between economy and economy plus, which suggests that maybe those few extra inches of legroom in economy plus really aren't doing that much for probability of satisfaction. We're not limited to numeric inputs. We can look at categorical ones as well. So here's how we would interpret this particular partial dependence plot. We actually have two categorical inputs that we're looking at: type of travel and the type of customer. The shading of the box represents the probability of satisfaction. So darker blue indicates lower satisfaction than lighter blue. Now in general, customers traveling for personal reasons tend to be less satisfied than customers traveling for business reasons. Looking at whether or not a customer is loyal versus disloyal. So loyal would be someone with, say, a club membership, someone who flies on that airline frequently. They tend to be more likely to be satisfied than the disloyal customers on the left. So we see sort of a two-dimensional relationship here to the satisfaction. There are some advantages to these partial dependence plots. First, these are really intuitive to compute. We're just looking at the average prediction. We force all data points to take on a particular feature value, so we're averaging over everything else in the background. That makes them easy to produce, and that makes them flexible. We can use categorical inputs or numerical inputs. Disadvantages, because we're visualizing, there's only two features that we can visualize at a time. The feature distribution may be omitted. So what that means is that we can look at this distribution of distance, for example, represented with these little hash marks here. This is the overall distribution of distance. We can't really see that as well for the travel types. We have some size of bars, but these aren't as easy to represent. We have no sense for the distance or distribution of class. So how many travelers are business, economy plus. So that's one disadvantage here. Assuming that variables are independent, that's the other big advantage. That is often not very realistic. So individual conditional expectation plots are another option. You can think of these as the partial dependence plot sort of broke apart. So what these do is visualize the dependence for each individual instance separately. So each observation has its own line in this individual conditional expectation plot. The advantages here, we can see how the predictions are going to change for each individual instance. The major disadvantage is that these get really overcrowded. So here's an example of that that individual conditional expectation plot. You can see here that we have a lot of observations. It's really difficult to tell over all of these individual observations what the predicted relationship between distance and satisfaction truly is. One nice addition, and I often recommend doing this if you're going to create these sort of plots, is to add the partial dependence line on top of it. Here I've done that by writing method equals PDP plus ice. This yellow line then represents the partial dependence. So all of the black lines sort of average together. In general, we can see that as distance is increasing, there's a slight increase in the predicted satisfaction. Unfortunately, we don't know what these observations up here with high predicted satisfaction have in common, nor do we know what the ones with low satisfaction have in common. Now, if we're in that situation where the features are correlated, we might not want to use the partial dependence plot. The solution here is to rely on accumulated local effects or ALE plots instead. With these, we split the data into bins. So we split it up into small groups, and then within each bin, we'll calculate the difference in predictions based on conditional distribution of the features. So these are showing you how the model predictions are changing within a very small window of the feature. These ALE plots are looking at average changes of predictions, so they're not looking at the average predictions themselves. That means that the average effect is going to be 0. So we're looking for areas where the prediction is higher than normal, and the areas where the prediction is lower than normal. So here's what that ALE plot looks like for distance. Looking at smaller distances here, there's a negative effect on satisfaction, whereas larger distances, there's a positive effect on satisfaction. We can do the same thing looking at class versus distance. Again, that negative effect indicated here in darker regions, business class short distance tends to be less satisfied. Economy class higher distances tend to be less satisfied. Advantages of these ALE plots. These are unbiased, so these will work with correlated features. These are actually a bit faster to compute as well, and they're centered at 0. So this negative versus positive effect is very intuitive to calculate. Disadvantages here. The big one is the second one. The accuracy of these estimates depends on the number of instances in each bin. So for the second plot, if we look at how accurate this is, maybe there's only a few business class trips over short distances. That would certainly affect how confident we are about these effects, but that information really isn't readily available. At the time of writing these slides, these weren't yet implemented for 2 categorical variables. That may have changed. So we will pause here. We'll jump back into these plots in part 2 of this video.